Hi, my name is Robert Lee, and the main goal of this video series is to provide beginners with basic LoRa and LoRaWAN knowledge. For educational purpose, I try to simplify things, but do not expect an in-depth explanation of each subject matter. I am focusing on the concept and not the details. In this first tutorial, I will explain why LoRa is used in IoT projects. The Internet of Things, or IoT, is a network of physical devices that are connected to the Internet and are able to talk to each other. The prediction is that by 2020 there will be over 25 billion devices connected to the Internet. There are many wireless technologies you can use to connect these devices to the Internet, such as short-range wireless communication, cellular communication, or LPWAN communication. In this video series, I will be using equations and other information taken from several sources. In my presentations, these sources are referenced by a label starting with a square bracket, a reference number, and closed by a square bracket. For this video series, I will be using these references. And also this reference. All my presentations used in this video series can be found at this location. LPWAN stands for Low Power Wide Area Network, and this type of wireless communication is designed for sending small data packages over long distances operating on a battery. There are a number of competing technologies in the LPWAN space, such as Narrowband IoT, Sigfox, LoRa, and others. As you can see in this picture, LPWAN is located in this area, cellular communication is located in this area, and the short-range wireless communication is located in this area. LoRa is located here. As you can see, long distance and sending small data packages. In this video series, I will only be focusing on LoRa. To give you an idea how these wireless technologies compare to each other, here is Bluetooth, Wi-Fi, 3G and 4G, and LoRa. Bluetooth and Wi-Fi have clearly short ranges compared to cellular and LPWAN. But as you can clearly see, cellular uses a lot of transmission power compared to LoRa. LoRa cannot be used to send video or audio messages. You can only use LoRa to send very small data packages, such as sensor data, for example, temperature data, humidity data, etc. The main selling point of LoRa is long distance and using a very low transmission power, average 20 milliwatts. The LoRa wireless technology was developed by a French startup company, Cycleo, which developed the LoRa modulation technology. In 2012, the Semtech Corporation acquired Cycleo. The LoRa radio and modulation part is patented and its source is closed. Semtech has licensed its LoRa intellectual property to other chip manufacturers such as Hope RF, Microchip, Dorji, etc. The word LoRa is a trademark of Semtech Corporation filed in 2015. More information about Semtech can be found at this location. The range between LoRa sender and receiver depends on the environment the equipment operates in. Indoor coverage largely depends on the type of building material used. To give you an indication, urban areas, the range is between 2 to 5 kilometers, rural areas, 5 to 15 kilometers, and if there are no obstacles and you have direct line of sight, you can achieve a distance of greater than 15 kilometers. But please note, these ranges can only be achieved if certain conditions are met. What these conditions are will be explained in detail later in this video series. But here are some notable records. Andreas Spies, a fellow YouTuber and known as man with a Swiss accent, has conducted an experiment and he achieved a LoRa ground-to-ground connection over a distance of 212 kilometers. Another team also created another record whereby a LoRa sender is connected to a weather balloon. Several LoRa receivers on the ground detected the signal. At a distance of 702 kilometers, a receiver was able to detect the signal. These records can only be achieved if there is direct line of sight and there are no obstacles within the Fresnel Zone, which I will explain what it is later in this video series. Here are a few use cases using LoRa technology. I have created 5 categories: smart utilities, health and hygiene, safety, efficiency, and agriculture. And for each category, you will find a few use cases. In the category smart utilities, you can use the LoRa technology in power transformer monitoring, water level monitoring, utility meter, and fuel monitoring. With fuel monitoring, I mean monitoring fuel levels in fuel tanks for heating houses. In the category health and hygiene, temperature and humidity monitoring, environmental monitoring, and waste management, meaning monitoring waste levels in waste bins. In the category safety, smart lighting, water level monitoring, radioactivity level monitoring, and dike monitoring, for example, to prevent peat dikes from drying out. This can be applied, for example, in the Netherlands, where we have a lot of peat dikes. In the category efficiency, we have asset management and fleet management. For example, tracking cars, vans, and trucks. And the last category, agriculture, monitoring animal welfare and monitoring plant growing conditions. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain what the difference is between LoRa and LoRaWAN. Several products will be shown in this video. They are not paid endorsements. I have bought all these products myself. There are many Alora Gateway and LoRa development board manufacturers. If you plan to buy such products, do your own research. LoRa is an acronym for long range, and it is a wireless technology where a low-powered sender transmits small data packages between 0.3 kilobits per second to 5.5 kilobits per second to a receiver over a long distance. A gateway can handle hundreds of devices at the same time. A LoRa end node consists of 2 parts: a radio module with antenna, a microprocessor to process, for example, the sensor data. This is a LoRa development board. Here is the radio module. Here is the antenna printed on the circuit board, and here is the microprocessor. End nodes are often battery powered. A LoRa device has a wireless transceiver. If this device also has sensors, this device acts as a remote sensor. Such a device is called a mode, short for remote. Here's an example of a LoRa development board. And here is an example of a LoRa node. As you can see, it is battery powered. This LoRa node can measure the temperature. It also detects if a push button is pressed. This button. When you shake this node, it will detect this motion. A LoRa gateway consists of 2 parts: a radio module with antenna, a microprocessor to process the data. The gateways are mains powered and connected to the internet. Multiple gateways can receive data from the same end node. The gateways can listen to multiple frequencies simultaneously in every spreading factor at each frequency. Here's an example of a gateway. This particular gateway has an Ethernet port. It is mains powered. As you can see over here. And it has an antenna. And this is the radio module part. A LoRaWAN network architecture is deployed in a star topology. Here are the end nodes. These are the gateways or concentrators. This is a network server, and these are the application servers. The communication between the end node and gateway is bidirectional, which means the end node can send data to the gateway, but it can also receive data from the gateway. So the end node can send data to the gateway, to the network server, and to the application server. but you can also send data from the application server to the network server, to the gateway, to the end node. Communication from end node to gateway is called an uplink. Communication from gateway to end node is called a downlink. An end node broadcasts its data to every gateway in its vicinity. For example, this end node is a water meter, and it sends its data to this gateway and to this gateway. The gateways forwards this package to the network server. The network server collects the messages from all the gateways and filters out the duplicate data and determines the gateway that has the best reception. The network server forwards this package to the correct application server, for example this one, where the end user can process the sensor data. When a response is sent, the network server receives the response and determines which gateway to use to broadcast the response back to the end node. For example, the network server determines that this gateway is the best gateway to send the response back to the water meter. The LoRaWAN protocol does not support direct communication between end nodes. If you want direct communication between LoRa devices without the use of gateways, use the Radiohead Packet Radio Library for embedded microprocessors. It provides a complete object-oriented library for sending and receiving packet-sized messages via a variety of radios such as LoRa on a range of embedded microprocessors. You can find this library at this location. Radiohead does not have an official GitHub repo, but several people have cloned the Radiohead library on GitHub. This is the LoRa protocol stack. This is the application layer, the media access control layer, the physical layer, and the radio frequency layer. And here is the difference between LoRa and LoRaWAN. LoRa is the physical layer, meaning the radio and the modulation part, and LoRaWAN is the media access control layer, specifying class A, B, and C devices, which I will explain in a later video, and the application layer. The LoRaWAN protocols are defined by the LoRa Alliance. It is a non-profit organization of more than 500 member companies committed to enabling large-scale development of LPWAN IoT through the development and promotion of the LoRaWAN open standard. More information about the LoRa Alliance can be found at these two locations. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain who sets the wireless communication rules and regulations. LoRa operates in the unlicensed ISM radio band that are available worldwide. ISM stands for Industrial, Scientific, and Medical. For example, in Europe, the ISM frequency band ranges from 863 to 870 MHz, and in the United States, the ISM frequency band ranges from 902 MHz to 928 MHz. Let's look at these two web pages. This is the Things Network website. I live in the Netherlands, so I click the letter N. As you can see, it uses this frequency range. If I select this link, Overview, and I search for this frequency plan, I can clearly see which frequency I can use. This is for uplink messages, and this is for downlink messages. For now, ignore these values. I will explain this in later videos. Let's go back. For example, if you live in the United States, here you can see it uses this frequency range. Let's go back to Overview. These are the frequencies used in the United States. Here are the frequencies for the uplink messages, and here are the frequencies for the downlink messages. As mentioned earlier, in the United States, LoRaWAN operates in the 902 to 928 MHz frequency band. Let's look at the United States frequency allocation. Here is the United States frequency allocations. It starts from 3 kHz to 900 GHz. Let's zoom in. It starts from 3 kHz to 300 GHz. As you can see, this radio spectrum is allocated for many different uses. For example, this frequency range is allocated for radio navigation, and this frequency range is allocated for TV broadcasting. Let's see where the 902 to 928 MHz ISM band is located. Let's zoom in. 902 to 928, and it is clearly marked over here, 950 MHz plus minus 13 MHz. This is the frequency range used by LoRa within the United States. In the European Union, LoRa uses the 863 to 870 MHz frequency range. That is this range. As you can see, in the United States, this frequency range is allocated for land mobile radio systems. For example, two-way radios in vehicles. If you buy a LoRa development board, always buy one with the correct frequency which applies to your country. If you buy the wrong frequency, you break the law and it will not work. The same applies to the gateway. I live in the Netherlands, so I have to buy a gateway using this frequency. If you build your own LoRa node, you can buy these radio modules. This is such a radio module. And as you can see, I have bought one with 868 MHz. Never buy the wrong frequency. Devices such as microwave ovens, medical equipment, or baby monitors all uses the ISM band. Here are ISM band advantages. Anyone is allowed to use these frequencies and no license fee is required. And here are ISM band disadvantages: low data rate and lots of interference because anyone can use these frequencies. Because the ISM band can be used by everyone, there must be some rules set, otherwise this band will become unusable. Think of the many signal interferences. There are several international organizations which manage the radio spectrum to ensure safe coexistence between all the different radio technologies. In Europe, the European Telecommunications Standard Institute, ETSI, creates standards which are used by local regulatory authorities, meaning countries. More information about ETSI can be found at this location. In the United States, the Federal Communications Commission, aka FCC, creates these standards. More information about FCC can be found at this location. All other countries are using the standard set by either ETSI or FCC. Except Japan, they have the Telecom Engineering Center, and South Korea, they have the Korean Communications Commission. For example, in the Netherlands, its telecommunication regulatory authority is called the Telecom Agency, in Dutch Agentschap Telecom, which is part of the Ministry of Economic Affairs and Climate, in Dutch Ministerie van Economische Zaken en Klimaat. This regulatory authority has issued the conditions and requirements when using LoRa in the Netherlands and is based on the standards set by ETSI. More information about the Dutch LoRa conditions and requirements can be found at these two locations. Let's only focus on ETSI and FCC. Here are two geographic areas, in this example Netherlands and China, where the ETSI regulatory domain is used. And here are two geographic areas, in this case United States and Australia, where the FCC regulatory domain is used. If I focus on the Netherlands, this national regulatory authority uses the standard set by ETSI, but they can also add additional rules. Here you see the network operator. There are commercial or non-commercial operators who can set up a LoRaWAN network. These operators can set additional rules. For example, in Europe, when using the ISM band frequencies 863 MHz to 870 MHz, users must comply to the following rules. For uplink, the maximum transmission power is limited to 25 mW or 14 dBm. For downlink, for 869.525 MHz, the maximum transmission power is limited to a half watt or 27 dBm. there is a 0.1% and 1% duty cycle per day depending on the channel, and the maximum allowed antenna gain is 2.15 dBi. Besides these ISM band rules, the network operator, for example the Things network, can also add additional restrictions. If you use the Things network, which is a free public community LoRaWAN network, the following fair use policy applies. The uplink airtime is limited to 30 seconds per day per node, and the downlink messages are limited to 10 messages per day per node. More information about the Things network fair use policy, go to this location. When a signal is sent from a sender, it takes a certain amount of time before a receiver receives this signal. This time is called time on air. Here is the sender and here is the receiver. Here is the sender with a transmission radio and here's the antenna. And here's the receiver with the receiver radio with an antenna. In this example, it takes 530 milliseconds to travel from this antenna to this antenna. So the 530 milliseconds is the time on air. Duty cycle is the proportion of time during which a component, device or system is operated. The duty cycle can be expressed as a ratio or as a percentage. As mentioned previously, in Europe there is a 0.1% and 1% duty cycle per day depending on the channel. For example, time on air is 530 milliseconds and the duty cycle is 1%. So the 530 milliseconds is the time on air, which equals 1%. So 99% of the time, which is the same as 52.47 seconds. And this is the amount of time you have to wait after you have sent a signal. So after you have waited 52.47 seconds, you can broadcast the same signal again, meaning the same size signal. Here's another example. Time on air is 400 milliseconds. And now the duty cycle is 0.1%. So 400 milliseconds represents 0.1%. So 999 times this time on air equals 399.6 seconds. So after you have sent this signal, you have to wait 399.6 seconds before you can send the same signal again. So why is this duty cycle rule set? If there were no duty cycle, then anyone can broadcast at unlimited time, which renders the usage of the ISM band completely unusable. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain what LoRaWAN devices are. The LoRaWAN specification defines three device classes. Class A, which stands for all, Class B, which stands for beacon, and Class C, which stands for continuous. Class A are battery-powered devices. Each device uplinked to the gateway and is followed by two short downlink receive windows. Class B is the same as Class A, but these devices also opens extra receive windows at scheduled times. Class C devices are the same as Class A, but these devices are continuously listening. Hence, these devices uses more power and are often mains powered. The reason why this is called all is because all device classes, B and C, can also behave like a Class A device. The reason why this is called beacon is because beacons are used, which I will explain later on. The reason why this is called continuous is because these devices are continuous listening. Now let's look at these device classes in detail. First, let's start with Class A. At any time, an end node can broadcast a signal, this signal. After this uplink transmission, the end node will listen for a response from the gateway. The end node opens two receive slots at T1 and T2 seconds after an uplink transmission. The gateway can respond within the first receive slot or the second receive slot, but not both. So a gateway can respond within this slot or within this slot, but not both. Now let's look at Class B devices. In addition to Class A receive slots, Class B devices opens extra receive slots at scheduled times. As you can see over here, Class B devices also incorporates Class A behavior with its standard 2 receive slots. And here are the extra receive slots opened at scheduled times. The end node receives a time-synchronized beacon from the gateway, allowing the gateway to know when the node is listening. In this picture, you see two time-synchronized beacons from the gateway, which are received by the end node. A Class B device does not support device C functionality. Last, let's look at Class C devices. In addition to Class A receive slots, a Class C device will listen continuously for responses from the gateway. As you can see over here, Class C devices also incorporates Class A behavior with its standard 2 receive slots. And after these 2 receive slots, Class C device will continue listening for responses from the gateway until the next uplink transmission. A Class C device does not support device B functionality. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain what the decibel is and what the purposes are of the units dBm, dBi, and dBd. A decibel is a unit of measurement used to express the ratio of powers, sound pressures, or other things on a logarithmic scale. The decibel was invented by Bell Labs and named after Alexander Graham Bell. In this tutorial, the decibel is used to express the ratio of electrical powers, meaning watts. Here is an equation to calculate the decibel value, where Pi is the input power and Po is the output power. For example, if this is an amplifier, this is the input power and this is the output power. Because the output power is greater than the input power, it is a gain. To calculate the decibel value, the equation is now 10 times log base 10 of 3, this is the output power and this is the input power, equals 4.7 dB. Here's another example. The input power is 10 milliwatt, the output power is 8 milliwatt. So in this example, there is a loss. Because the output power is less than the input power, the equation is now 10 times log base 10 of 0.8 equals minus 0.96 dB. Please note, if it is a positive value, it is a gain. If it is a negative value, it is a loss. To convert the decibel value to a power ratio, you can use this equation. The logarithmic scale is used to avoid very big or very small numbers, meaning the ratios. Using decibels is easier to work with. For example, a power ratio of 1 million can be expressed by 60 dB. A power ratio of 1 millionth can be expressed by minus 60 dB. A power ratio of 1 quadrillion can be expressed by 150 dB. A power ratio of 1 quadrillionth can be expressed by minus 115 dB. A power ratio of 1 septillion can be expressed by 240 dB. A power ratio of 1 septillionth can be expressed by minus 240 dB. As you can see, instead of writing this large number, you can write this small number. So it is easier to work with small number instead of these big numbers. Please note, this is a ratio. For example, let's say my salary is twice of a teacher's salary. Do you know what my salary is? No, you don't. You only know that my salary is twice of a teacher's salary, but you don't know my actual salary. And that is the ratio. This is not an absolute value. It is a ratio. In this example, it means 1 million, but you don't know what the absolute power is. So remember, the unit dB is a ratio. It does not represent an absolute value. If you look at this device, the only thing you know about this device is that it has a gain of 3 dB. You don't know its input power and you don't know its output power. Question: if the input power is 1 milliwatt, do you know what the output power is if you use this example? Yes, you know what the output power is. You can use this equation. The input power is 1, so the output power is 1.995 milliwatts. dB is a ratio. It does not represent an absolute value. If we use a reference input power of 1 milliwatt, the unit is expressed as dBm. Here are two equations. This equation is used to calculate the decibel value, and as you can see, the input power is 1 milliwatt. If the input power is 1 milliwatt, the unit is now dBm. And this is the equation to convert the decibel value into a power ratio. And if the input power is 1 milliwatt, the equation can be rewritten like this. The unit dBm represents an absolute value because it uses a fixed reference value of 1 milliwatts. The unit dB is a ratio. The unit dBm is an absolute value. Here are three examples. This transmitter has a gain of 80 dBm. The power output is calculated with this equation. As you can see, the value 80 is entered here. And the output power is 100 kilowatts. This transmitter has a gain of 27 dBm. The equation now looks like this. 27 is entered here. The output power is 500 milliwatts. And as you can see over here, the receiver has a loss of minus 73 dBm. The equation looks like this. Minus 73 is entered here. So the power output is 5 times 10 to the power of minus 8 milliwatts. There is an easy way to convert dBm values to its absolute power value. Remember the rule of tens and threes. If you see 10 dB, it means multiply by 10. If you see minus 10 dB, you need to divide by 10. If you see 3 dB, you need to multiply by 2. And if you see minus 3 dB, you have to divide by 2. But where does these values come from? Here are a few positive decibel values, and here are a few negative decibel values. If we use this equation, we can calculate its power ratios. 3 dB represents a power ratio of approximately 2. 10 dB represents a power ratio of 10. A power ratio of minus 3 dB represents a power ratio of a half, and minus 10 dB represents a power ratio of 1/10. So a power ratio of 2 means times 2. A power ratio of 10 means times 10. A power ratio of a half means divided by 2. Power ratio of 0.1 means divided by 10. This value, this value, this value, and this value is where the rule of tens and threes come from. 3 dB is not exact a power ratio of 2. It is 1.995, but we round it to 2. The same applies to minus 3 dB. Minus 3 dB is not exactly 0.5. It is 0.501. We round it to 0.5. So the power ratios belonging to 3 dB and minus 3 dB are both rounded values. You can calculate any number by only using the values 10 and 3. For example, 1 can be calculated by 10 minus 3 minus 3 minus 3, that is 1. The value 2 can be calculated as follows: 3 plus 3 plus 3 plus 3 minus 10, that is 2. Well, 3 is 3. 4 can be calculated as follows: 10 minus 3 minus 3, that is 4. 5 can be calculated as follows: 3 plus 3 plus 3 plus 3 plus 3 minus 10 is 5. So you get the idea. Try the rest yourself. Here are more examples. And here are a few difficult ones. The rules are only use a multiple of tens and threes. You can use positive and negative values to represent a value. If possible, avoid using threes and never use more than 5 threes. Do you know why? It's because of the rounding I have explained earlier. So this is incorrect. The value 8 should not be represented by 3 plus 3 plus 3 plus 3 plus 3 plus 3 minus 10 because it uses more than 5 threes. It uses 1, 2, 3, 4, 5, 6. Correct way is this. 10 plus 10 is 20, minus 12 is 8. As you can see, we only use 4 threes. If a transmitter has 6 dBm, how much power does it generate? The answer is, we know that the input power is always 1 milliwatts. Remember the m in dBm, which means we are using an input power of 1 milliwatt. So 6 dB can be written as 3 dB plus 3 dB. We start with 1 milliwatt, and 3 dB means multiply by 2. Remember the rule of tens and 3. Multiply by 2 and multiply by 2. So 1 milliwatt times 2 is 2 milliwatt, times 2 is 4 milliwatts. So 6 dBm is approximately 4 milliwatt. Another example. If a transmitter has 17 dBm, how much power does it generate? The answer is we start with 17 dB, which can be written as 10 dB plus 10 dB minus 3 dB, which is equal to 17 dB. We start with 1 milliwatt. 10 dB means multiply by 10. As you can see over here. Multiply by 10, and this means divide by 2. We start with 1 milliwatt. Multiply by 10 is 10 milliwatt. Multiply by 10 is 100 milliwatt. Divided by 2 is 50 milliwatts. So 17 dBm is approximately 50 milliwatts. Here is another example. The receiver has a sensitivity of minus 138 dBm. How much power is this? We start with minus 138 dB. Minus 138 can be written as this. If you calculate these values, it is minus 100. If you calculate these three values, it's minus 30. If you calculate these values, it is minus 8. So total is minus 138. Again, we start with 1 milliwatt. So minus 10 means divided by 10, and plus 3 means multiply by 2. So we start with 1 milliwatt, as you can see over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 to the power of minus 10. 1, 2, 3. Times 10 to the power of minus 3. 1, 2. Times 10 to the power of minus 2. 2, 4, 8, 16. Times 16. Minus 10, minus 3, minus 2. That is minus 15. So minus 138 dBm is approximately 16 times 10 to the power of minus 15 milliwatts. If we want to convert this value into watts, that is this value, which is approximately 16 times 10 to the power of minus 18 watt. Here are prefixes used with SI units. SI is French for Système International, which means International System of Units. These units can be used, for example, for powers, for distances, for time, etc. For example, minus 138 dBm is approximately 16 times 10 to the power of minus 18 watts, which is the same as 16 attowatts. Here's another example. Please try to convert this dBm value to its corresponding power. Other notable decibel notations are dBi and dBd. These also represents ratios. Antenna manufacturers are using these units to measure antenna performance and is useful for comparison purpose. For example, manufacturer A has an 868 MHz antenna. Its gain is 3 dBi. Manufacturer B has an 868 MHz antenna. Its gain is 2.5 dBi. Looking at this example, manufacturer A has an antenna which has a better gain compared to manufacturer B. dBi refers to the antenna gain with respect to an isotropic antenna. This is an hypothetical point source antenna that radiates its power uniformly in all directions. This point represents an isotropic antenna. This isotropic antenna does not exist in reality. And this is the radiation pattern of this point source. Radiation or antenna pattern reflects the strength of the radio waves from the antenna in different directions. dBd refers to the antenna gain with respect to a reference dipole antenna. This is what the dipole antenna looks like. These are two metal rods, and each metal rod is a quarter wavelength in size. This is a radiation pattern of a dipole antenna. It looks like a donut. The relationship between dBd and dBi can be expressed with this equation. As you can see over here, the isotropic antenna sends the signal out in every direction. A dipole antenna focuses the signal more on a horizontal plane perpendicular to the dipole antenna. This is the radiation pattern of an isotropic antenna. This point represents an isotropic antenna. This represents the dipole antenna. And this is the radiation pattern of a dipole antenna. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain what radio propagation and free space loss are. Propagation is the way how radio waves travels through free space, also known as medium. The way how these waves travels may impact its signal strength. Here are some examples. Line of sight propagation. The radio waves travels directly from sender to receiver without any obstacles. From end node to gateway, there are no obstacles. If the distance between sender and receiver gets larger, the signal gets weaker. This loss is known as free space loss. But even if there is a direct line of sight, you must always consider the Fresnel zone. I will explain what the Fresnel zone is in detail in the next video. But for now, this is the Fresnel zone, this is the ground. And in this particular example, the ground is an obstacle within the Fresnel zone. If this is the case, the radio waves reflecting off those objects, in this case the ground, may arrive out of phase with the signals that travel directly and reduce the power of the received signal. So this is the direct signal, this is the reflected signal, and these two signals are out of phase. Because of this, the signal strength is reduced. There's also propagation through obstacles. Radio waves may penetrate through obstacles that appear in its path. Radio waves lose strength if it travels through obstacles made of more conductive materials. If you look at this picture, we have three end nodes. In this case, signals go through buildings. In this case, signals go through trees. And in this case, there's a mountain between the end node and the gateway. Buildings are made of more conductive materials, which weakens the signal compared to trees. A mountain blocks the signal completely. There's also propagation through reflection. Radio waves can be reflected by buildings which interfere with its direct signal. Here's an end node, and this is a direct signal to the gateway. If there's a building, the signal can be reflected. The reflected signal can interfere with the direct signal. You also have propagation through diffraction. Diffraction is where radio waves are bent around sharp edges. A signal from a transmitter may be received by the gateway, even though it may be shaded by a large obstacle. In this example, the gateway receives a diffracted signal, but not the direct signal. There are more types of propagations which impact the signal strength, but the ones explained in this video, meaning line of sight propagation, propagation through obstacles, propagation through reflection, and propagation through diffraction, are the important ones. I have already explained what free space loss is, but you can calculate the free space loss using this equation. The free space loss is expressed in decibels, and it depends on its distance between end node and gateway and the frequency. And here are some calculations using the 868 MHz frequency. This is 10 meters, 50 meters, 100 meters, 500 meters, and 1 kilometer. And you can see the corresponding free space loss. In a later video, you will see that the free space loss is the biggest loss in a radio communication system. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain what the Fresnel Zone is. The Fresnel Zone is an elliptical-shaped body around the direct line of sight path between the end node and the gateway. Any obstacle within this volume, for example buildings, trees, hilltops or ground, can weaken the transmitted signal even if there is a direct line of sight between the end node and the gateway. The maximum radius of the Fresnel zone, located half the distance between end node and gateway, is calculated using this equation. Here is the end node and here is the gateway. This is the distance between end node and gateway, and this is called the Fresnel zone. This radius is calculated with this equation, and this radius is located at half the distance. As you can see in the equation, if the distance increases, the radius increases. This distance is called the Fresnel zone clearance. In this picture, you can see that the end node can send signal to the gateway without any interference, because there are no obstacles within the Fresnel zone. But if you change the distance between end node and a gateway, for example increasing the distance, the radius will increase in size. The ground will be inside the Fresnel zone, which means the signal can be reflected, which interferes with the direct signal. The same can happen if you change the end node and/or gateway vertical position. This is the direct signal from end node to gateway, and these two are the reflected signals. In this graph, the direct and reflected signals are in phase. The direct signal will be enhanced. In this graph, the direct and reflected signal are out of phase. The direct signal will be cancelled out. In general, avoid objects within the Fresnel zone, because it has a negative impact on your signal strength. So how can you avoid objects within the Fresnel zone? Well, place the antenna at a higher location, as you can see over here. Here's your end node, here's your gateway, and as you can see, there are no objects within the Fresnel zone. In this example, the end node sends a signal to the gateway without any interference, because there are no obstacles within the Fresnel zone. The Fresnel zone equation is based on a flat Earth. It does not take the curvature of the Earth into consideration. If your end node is located here and your gateway is located here, and the distance between the two is very large, then this height must be taken into consideration. To calculate the height, you can use this equation. Here are some calculations. If the distance between end node and gateway is 2 kilometers, then the height is negligible. But if the distance is 5 kilometers or more, then the height plays an important role. As you can see, if the distance is 30 kilometers, the height is 13.2 meters. As a rule of thumb, Fresnel zone should always be clear of obstruction, but this can be impractical, so it is said that beyond 40% blockage, signal loss will be significant. So this area represents a Fresnel zone which is 60% clear, and this area represents a Fresnel zone with a 30% blockage. This means you can have objects within this 40% blockage area. This radius representing the 60% clearance can be calculated with this equation. So again, 60% clearance, this is the 40% blockage, and this is the Earth curvature. So objects within this green area are allowed. I have done some calculations. Let's take a frequency of 868 MHz. H is the Earth curvature allowance. This table represents 100% clearance, meaning there are no obstacles within the Fresnel zone. This radius is calculated with this equation. And this table represents a 60% clearance. This radius is calculated with this equation. This column and this column is the Fresnel zone radius plus the Earth curvature allowance. If you look at this example, the distance between end node and the gateway is 1 kilometer. This value means that the end node and gateway must be positioned 9.29 meters above ground if you don't want the ground to interfere with your signal. If the distance between end node and the gateway is 10 kilometers, the end node and gateway must be positioned 30.88 meters above ground if you don't want the ground to interfere with your direct signal. If you look at this table and you allow 60% clearance, and if the distance between end node and gateway is 10 kilometers, then end node and gateway must be positioned 24.26 meters above ground. If the vertical position is less than this value, then the ground will interfere with your direct signal. For the best radio signal performance, do the following. The gateway antenna must be placed outdoors at a high location, avoiding obstacles in the Fresnel zone. The antenna designed for both gateway and end node must be optimized for its regional frequency. And keep the antenna polarization vertical for both gateway and end nodes, and use omnidirectional antenna to cover a large area. As indicated here, place the gateway antenna at a high location. The antenna polarization for gateway and end node must be the same. In this example, the antenna polarization is horizontal, which is not good. This is the Things network map. These are all LoRaWAN gateways using the Things network. Let's zoom in. I'm located here, and as you can see, there are two gateways. The distance from here to here is 1.2 kilometers or 0.75 miles, and the distance from here to here is 1.6 kilometers or 1 mile. I have conducted some tests and I cannot reach this gateway with my end node, but I can reach this gateway. Why is this? As you can see, the gateway altitude is 10 meters above ground. However, this gateway is placed indoors. My end node is located 10 meters above ground, and most buildings from here to here are also 10 meters high, which means I do not have direct line of sight, and there are many obstacles within my Fresnel zone. If I look at this gateway, it's located 42 meters above ground. I have almost a direct line of sight with this gateway, and there are only a few obstacles within my Fresnel zone, and that is why my end node can reach this gateway. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain what link budgets, maximum link budgets, and link margins are. But first I need to explain what modulation and demodulation means. If an input signal, aka message, is imposed onto a carrier signal, for example this carrier signal, this process is called modulation. The modulated signal is broadcasted to the receiver. This is the modulated signal. Demodulation is the opposite, where the original signal is recovered from the modulated carrier wave. A link budget is a sum of all of the gains and losses from the transmitter, through the medium, to the receiver in a telecommunication system. It is a way of quantifying the link performance. Everything what is green, this, and this are gains, and everything what is red, this, and this are losses. The radio transmitter value must be specified in dBm, otherwise you do not know its absolute value. This cable including connectors and this cable including connectors, and the signal propagating through the medium are all losses, and these values are expressed in the unit dB. When a signal propagates through the medium, the signal loses strength. This is called the path loss or path attenuation. A well-designed antenna usually increases the signal strength. The received power, also known as Received Signal Strength Indication or RSSI, is a sum of the transmitted power plus all the gains and losses. The received power is plus 20, minus 5, plus 10, minus 115, plus 12, minus 2 equals minus 80 dBm. Please note, these values are not realistic values. These are just made up. The receiver sensitivity is the lowest power level at which the receiver can receive or demodulate the signal. For example, the receiver sensitivity is minus 90 dBm. The difference between the receiver power and the receiver sensitivity is called the link margin. Again, the link margin is the received power minus the receiver sensitivity. If the received power is minus 80 dBm and the receiver sensitivity is minus 90 dBm, the link margin is 10 dBm, which is the same as 10 milliwatts. Question: there are two receivers, receiver A with receiver sensitivity minus 120 dBm and receiver B with receiver sensitivity of minus 130 dBm. Which receiver is better? The answer is receiver B, because it can demodulate a radio frequency signal at a lower power level. If the link margin is too big or too small, corrective actions can be applied to ensure the system will operate satisfactorily. The link margin must be positive. The received power must be greater than the receiver sensitivity and should be at least a few decibels for the receiver to successfully demodulate the signal. LoRa receivers are very sensitive and are offering a sensitivity down to minus 148 dBm due to the use of chirp spread spectrum. I will explain chirp spread spectrum in a later video. More information can be found at this link. The maximum link budget can be used as a baseline value to compare one radio to the next. To calculate the maximum link budget, you can use this equation. The maximum link budget equals the maximum transmitter power minus the lowest receiver sensitivity. For example, the maximum transmitter power is 20 dBm and the lowest receiver sensitivity is minus 148 dBm. In this example, the maximum link budget will be 168 dBm. This is the maximum transmitter power, which is 20 dBm. And this dotted line represents the lowest receiver sensitivity. In this example, it is minus 148 dBm. The maximum link budget will be 168 dBm. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain what AERP and ARP are. The effective isotropic radiated power, or AERP, is the total power radiated by a hypothetical isotropic antenna in a single direction. The AERP is the transmission power plus the antenna gain minus the cable loss, and the value is expressed in the unit dBm. We only focus on these three values. We don't use these values if we calculate the AERP. If we calculate the AERP, the antenna gain must be expressed in the unit dBi. In this example, the AERP is 20 minus 5 is minus 15, plus 10 is 25 dBm. The effective radiated power, or ARP, is a total power radiated by an actual antenna relative to a half-wave dipole rather than a theoretical isotropic antenna. If we want to calculate the ARP value, then we only focus on these three values: is the transmission power, the antenna gain, and the cable loss. Please note, if we want to calculate the ARP value, the antenna gain must be expressed by the unit dBd. In this example, the ARP value is 20 plus 7.85 minus 5 equals 22.85 dBm. This is the equation to calculate the AERP value, and this is the equation to calculate the ARP value. Both equations are the same, with the exception of the antenna gains. This antenna gain must be expressed in the unit dBi, and this antenna gain must be expressed in the unit dBd. The relationship between AERP and ARP can be expressed by this equation. So what is the purpose of ERP and AERP? Radio frequency transmitting systems must adhere to certain rules set by regulatory bodies such as FCC or ETSI. One of these rules are radio devices must not exceed certain ERP or EIRP values set by these regulatory bodies. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain what RSSI and SNR are. The Received Signal Strength Indication, or RSSI, is the received signal power in milliwatts and is measured in dBm. This value can be used as a measurement of how well a receiver can hear a signal from a sender. In this picture, I have not drawn the sender side, I'm only interested in the receiver side. This is the path loss, the antenna gain, the cable and connector loss, and this is the Received Signal Strength Indication, or RSSI. The Received Signal Strength Indication is measured in dBm and is a negative value. The closer to zero, the better the signal is. Typical LoRa RSSI values are: the minimum RSSI value is minus 120 dBm. If the RSSI value is minus 30 dBm, the signal is strong. And if the RSSI value is minus 120 dBm, the signal is weak. The signal-to-noise ratio, or SNR, is the ratio between the received power signal and the noise floor power level. The noise floor is an area of all unwanted interfering signal sources which can corrupt the transmitted signal, and therefore retransmissions will occur. In this picture, you will see two situations. In this situation, the SNR value is greater than 0, which means the received signal operates above the noise floor. And in this situation, the SNR value is smaller than 0, which means the received signal operates below the noise floor. What you now hear is the noise. You can clearly see that the received signal operates above the noise floor. So this is the received signal. Normally, the noise floor is the physical limit of sensitivity. However, LoRa works below the noise level. In this picture, this is the noise floor power level, and this is the received signal strength indication, aka received power level. And as you can see, the received power level is below the noise floor power level. Typical LoRa SNR values are between minus 20 dB and plus 10 dB. A value closer to plus 10 dB means the received signal is less corrupted. LoRa can demodulate signals which are minus 7.5 dB to minus 20 dB below the noise floor. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will discuss carrier frequencies, bandwidth, ETSI subbands, dwell time, and hop time. As mentioned before, LoRaWAN uses frequencies in the ISM band. On the Things Network website, you can find the carrier frequencies for your country. First, find the frequency plan which applies to your country. Go to this webpage. This webpage. For example, I live in the Netherlands. I select the letter N. As you can see, the Netherlands uses this frequency plan, AU 863 to 870 MHz. I now know the frequency plan. Select this link, Overview. And here you can find the frequency plans. And here are other frequency plans. Here are the upload frequencies. And here are the download frequencies. Instead of using the Things Network website, check out the LoRaWAN Regional Parameters document issued by the LoRa Alliance. Go to this webpage, and here you can download the LoRaWAN Regional Parameters document. This is the LoRaWAN Regional Parameters document. And here you can find the regional parameters for different ISM bands. For example, here is the AU 863 to 870 MHz ISM band, the US 902 to 928 MHz ISM band, etc. This document contains the approved frequency channel plans for various global regions and follows the established regulatory constraints in those regions. In this video, I'm only focusing on the AU 863 to 870 ISM band. For other ISM bands, please consult the LoRaWAN Regional Parameters document. In this table, you will find the LoRaWAN frequencies used in Europe, for example in the Netherlands. These uplink frequencies matches the Things Network frequency plan AU 863 to 870 MHz. Channel 0 uses this uplink frequency, Channel 1 uses this uplink frequency, Channel 2 uses this uplink frequency, etc. And for each uplink frequency, there is a corresponding spreading factor and bandwidth range, as you can see over here. I will explain spreading factors in another video. For example, this frequency uses the 125 kHz bandwidth. This frequency uses the 125 kHz bandwidth and also the 250 kHz bandwidth. All the other frequencies uses the 125 kHz bandwidth. And in this table, you will find the download frequencies. The download frequencies is the same as the upload frequencies for slot 1 and an additional download frequency to be used for slot 2. To recap, for upload links, there are 8 channels to use. For downlinks, the same 8 channels are used for receive slot 1 and 1 channel for receive slot 2. The receive slots are explained in tutorial 4, LoRaWAN device classes. If your country uses the AU 863 to 870 ISM band, then according to the LoRaWAN Regional Parameters document, every AU 868 MHz end device must implement the following default channels: 868.1 MHz, 868.3 MHz, and 868.5 MHz. All three uses the 125 kHz bandwidth, and additional 5 frequencies. The other 5 frequencies can be freely attributed by the network operator. For example, the Things Network implemented the following frequencies: 867.1, 867.3, 867.5, 867.7, and 867.9. Earlier, the word channel is used. A channel is just an agreed upon set of specific frequencies with additional information included in the agreement. For example, when using the Things Network frequency plan AU 863 to 870, the uplink channel 3 refers to carrier frequency 867.1 MHz and spreading factor 7 to 12, and all using the 125 kHz bandwidth. The LoRaWAN regional parameters used by the Things network can also be found at this GitHub page. This GitHub page. If you open this JSON file, for example, channel 0 uses this frequency and this bandwidth, and uses all spreading factors. Channel 1 uses this frequency, using this bandwidth, using all spreading factors, etc. In this picture, you see the LoRaWAN frequencies used in Europe, based on the Things Network frequency plan AU 863 to 870. Here are the 8 upload frequencies, and here are the 8 download frequencies to be used for slot 1, and an additional download frequency for slot 2. The orange and blue colors represents the 125 kHz bandwidth, and the green color represents the 250 kHz bandwidth. As you can see, the 250 kHz bandwidth is only used at this frequency. All frequencies uses the 125 kHz bandwidth. ETSI divides the 863 to 870 MHz band into 5 subbands, named G, G1, G2, G3, and G4. Each subband has different constraints in terms of EIRP, duty cycle, and channel bandwidth. For example, subband G1 represents this frequency band, and these are the limitations which are applied on this subband. In this picture, the subbands are mapped on the Things network AU 863 to 870 frequency plan. For example, subband G1, the EIRP is limited to 25 milliwatts and the duty cycle is 1%. These limitations apply to these 3 frequencies. LoRaWAN only uses the following bandwidth ranges: 125 kHz, 250 kHz, and 500 kHz. Which of these 3 ranges are actually used depends on the region or frequency plan. For example, in Europe, only the bandwidths 125 kHz and 250 kHz are used. The relationship between bandwidth and carrier frequency can be seen in the figure below. For example, if the carrier frequency is 867.1 MHz, for example, this is the carrier frequency, and for example, the bandwidth is 125 kHz, then the lowest frequency and the highest frequency can be calculated as follows. The lowest frequency is the carrier frequency minus the bandwidth divided by 2 equals this lowest frequency, and the highest frequency is the carrier frequency plus the bandwidth divided by 2 is this highest frequency. In this picture, you see the LoRaWAN frequency used in Europe based on the Things network frequency plan AU 863 to 870. Here are the uplink frequencies with corresponding bandwidths. These are actual LoRa transmitted signals. This is a LoRa transmitted signal using the 125 kHz bandwidth, and this is the LoRa transmitted signal using the 250 kHz bandwidth. An end device changes channel in a pseudo-random fashion for every transmission. Changing frequencies makes the system more robust to interferences. For example, in Europe, for uplink transmissions, 8 different frequencies are used, as explained earlier. Let's assume this blue color block represents a 15 bytes message, and this red color block represents an 8 bytes message. For example, this message is first transmitted at this frequency. Then after, let's say 1 minute, it transmits another message at this frequency. Then again, after a minute, it transmits this message at this frequency. And then again, it transmits this message at this frequency. As you can see, after every transmission, it hops to another frequency. Dwell time or transmit time is the amount of time needed to transmit on a frequency. So in this example, the dwell time is 3 milliseconds. Hop time is the amount of time needed to change from one frequency to another in which the radio is not transmitting. After this message is transmitted, it takes 1 millisecond to hop to another frequency. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain what the basic modulation types are and what chirp spread spectrum is. Modulation means how analog or digital information are encoded onto a carrier signal. When analog information are encoded onto a carrier signal, three modulation types can be used: amplitude modulation, frequency modulation, and phase modulation. When digital information are encoded onto a carrier signal, three modulation types can be used: amplitude shift keying, frequency shift keying, and phase shift keying. As mentioned earlier, an end node has a radio module. This radio module has a modulator which encodes information onto a carrier signal. This modulated signal is transmitted and received by a gateway. The gateway also has a radio module. This radio module has a demodulator which decodes the modulated signal and extracts the information. The communication between the end node and gateway is bidirectional, which means the end node can send data to the gateway, but it can also receive data from the gateway. If a device can both transmit and receive signals, this device is also called a transceiver. LoRa end nodes and gateways are transceivers. Now let's focus on modulating digital values onto a carrier signal. In this example, we have a digital message which we want to encode on this carrier signal. There are three basic modulation types: amplitude shift keying, frequency shift keying, and phase shift keying. When we use amplitude shift keying, only the amplitude changes. As you can see, the amplitude is here 3, and here the amplitude is 1.5. In this example, if the amplitude is 3, then it represents a digital 1, and when the amplitude is 1.5, it is a digital 0. When we use frequency shift keying, only the frequency changes. The signal here has a higher frequency than the signal here. This particular signal represents a digital 1, and this particular signal represents a digital 0. And when we use phase shift keying, only the phase changes. As you can clearly see, the phase of this signal is different than the phase of this signal. For example, when the signal has this phase, it represents digital 1, and when the signal has this phase, it represents digital 0. Besides the three basic modulation types, there are many other modulation types. LoRa is a proprietary spread spectrum modulation scheme that is based on chirp spread spectrum modulation. Chirp spread spectrum is a spread spectrum technique that uses wideband linear frequency modulated chirp pulses to encode information. Let's focus on the words spread spectrum technique and chirp. Spread spectrum techniques are methods by which a signal is deliberately spread in the frequency domain. For example, a signal is transmitted in short bursts, hopping between frequencies in a pseudo-random sequence. This is already explained in tutorial 11. And the chirp, often called a sweep signal, is a tone in which the frequency increases or decreases with time. If the frequency increases in time, it is called an up chirp, and when it decreases in time, it is called a down chirp. Here's an example of an up chirp where the frequency increases in time. Another way to visualize it: the lowest frequency is over here, the highest frequency is over here. The frequency increases in time. When the maximum frequency is reached, it jumps back to its lowest frequency and the process starts all over again. This is the up chirp. The down chirp is the inverse of the up chirp. It starts with its highest frequency and the frequency decreases with time. And when the lowest frequency is reached, it jumps back to its highest frequency and the process starts all over again. These chirp signals are used as carrier signals where a message is encoded on. Here is an actual LoRa modulated signal. This is the start of the message, and here is the encoded message. You can easily recognize the start of a message. It is a number of up chirps followed by 2 down chirps. Here is another LoRa modulated signal example. This is the start of the message, a number of up chirps followed by 2 down chirps, and here is the encoded message. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain what symbols, spreading factors, and chips are. The chirps are cyclically shifted, and it is the frequency jumps that determines how the data is encoded onto the chirps, aka LoRa modulation. This represents the unmodulated signal and this represents the modulated signal. And here you can see the frequency jumps. Here's an actual LoRa signal, and this is the start of the message because it has 10 up chirps followed by 2 down chirps. And here is the encoded message. As you can see, this symbol starts at this frequency, goes up, and when its highest frequency is reached, it jumps to its lowest frequency and the frequency increases till here. And the next symbol starts at this frequency and the frequency increases till its maximum frequency. It jumps to its lowest frequency, the frequency increases again, and it jumps to this frequency and the frequency increases and it reaches its maximum frequency here. A symbol represents 1 or more bits of data. For example, this symbol consists of 7 bits, representing decimal value 95. In the example above, the number of raw bits that can be encoded by the symbol is 7, which means the symbol consists of 7 bits. This is the same as saying spreading factor is 7. It also means the symbol has 2 to the power SF values. If spreading factor is 7, the values ranges from 0 to 127. The symbol value is encoded onto a sweep signal. Please note the following. What I'm now going to explain is a very simplified explanation, but it does not reflect the reality. But the explanation will give you the knowledge to understand the concept. Now let's continue. The sweep signal is divided into 2 to the power SF steps or chips. For example, the symbol is this, representing decimal value 95. The number of raw bits that can be encoded by the symbol is 7, meaning spreading factor is 7. The sweep signal is divided in 2 to the power of SF equals 2 to the power of 7, in this particular example, equals 128 chips. So what are these chips? Well, to keep this tutorial as simple as possible, take this sweep signal and chop it into 128 pieces and call each piece a chip. And if you order the chips in this arrangement, it represents decimal value 64. And if you order these chips in this arrangement, it represents decimal value 32. And if you order the chips in this arrangement, it represents decimal value 95. So this symbol holds 128 chips, which in this example represents decimal value 95. Another example, let's assume spreading factor is 12. Each symbol can carry 12 raw bits of information, and there are 2 to the power of 12 equals 4096 unique chip values ranging from 0 to 4095. The spreading factor defines two values: the number of raw bits that can be encoded by that symbol, meaning SF, and each symbol can hold 2 to the power SF chips. Please be aware of the difference between chirp and chip. A symbol holds 2 to the power of SF chips, and chirps are simply a ramp from F low to F high, meaning up chirps, or F high to F low, meaning down chirps. It is very important that you understand what symbols, spreading factors, and chips are, because in tutorial 15 I will discuss data rate, chip rate, and symbol rate, among others. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain what forward error correction and coding rates are. Forward error correction is the process where error correction bits are added to the transmitted data. These redundant bits helps to restore the data when the data gets corrupted by interference. If more error correction bits are added, the easier the data can be corrected. However, by adding more error correction bits, more data is transmitted, which decreases the battery life. The coding rate refers to the proportion of the transmitted bits that actually carries information. LoRa allowed coding rates values are 4/5, 4/6, 4/7, or 4/8. Here is another coding rate notation where CR can be the values 1, 2, 3, or 4. So if we say the coding rate is 1, we mean the coding rate is 4/5. If we say the coding rate is 2, we mean the coding rate is 4/6, etc. Let's assume the spreading factor is 8, which means 8 bits are transmitted. So if the coding rate is 1, then 6.4 bits carries actual information, as you can see by this calculation. 8 times 4/5 equals 6.4. So 6.4 bits carries actual information and the rest is for error correction. If the coding rate is 4, then 4 bits carries actual information, as you can see by this calculation. 8 times 4/8 equals 4. So 4 bits carries actual information and the rest is for error correction. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain how data rate, chip rate, symbol rate, chip duration, and symbol duration are calculated. Let's first start with the chip rate. The unit of bandwidth is Hertz, which is the number of vibrations or wave cycles per second. This bandwidth is interchangeably with chip rate. So the bandwidth is the same as the chip rate, and the chip rate is expressed in chips per second. For example, the bandwidth is 125 kHz, which is 125,000 Hz, so the bandwidth equals 125,000 chips per second. So the bandwidth is 125 kHz, which means it generates 125,000 chips per second. As I explained in tutorial 13, if the spreading factor is 9, the symbol carries 9 raw bits of information, and the symbol holds 2 to the power SF equals 2 to the power of 9 equals 512 chips. If the spreading factor is 9, this symbol holds 512 chips. The symbol rate is calculated using this equation. We now know that the bandwidth is the same as the chip rate, so the equation can also be written this way. Here's an example. If the bandwidth is 125 kHz and the spreading factor is 7, then the symbol rate is 125,000 divided by 2 to the power of 7 equals 977 symbols per second. This represents a single symbol. The chip rate is always higher than the symbol rate. To calculate the data rate, abbreviated with DR, or bit rate, abbreviated with RB, you can use this equation. By the way, data rate and bit rate are the same. The bit rate equals the spreading factor. This represents the number of raw bits each symbol carries, times the number of symbols per second, times the coding rate. The coding rate calculates the actual number of bits which carries information. Here are some examples. If the spreading factor is 7 and the coding rate is 1, then these are the bit rates for different bandwidths. If you increase the bandwidth, the bit rate or data rate is increased. Another example, the bandwidth is 125 kHz and the coding rate is 1. These are the calculated data rates for different spreading factors. If you increase the spreading factor, the bit rate or data rate is decreased. Because the chip rate is the same as the bandwidth, the chip duration is calculated using this equation. For example, if the bandwidth is 125 kHz, the chip duration is 8 microseconds. The symbol duration or sweep time is calculated using this equation. So this is a symbol, and this is its symbol duration. Here is another symbol, and this is its symbol duration. For example, the spreading factor is 7. Here are different bandwidths and the corresponding calculated symbol durations. As you can see, if the bandwidth increases, the symbol duration decreases. Here's another example. The bandwidth is 125 kHz. Here are 3 different spreading factors and the calculated symbol durations. As you can see, if the spreading factor increases, the symbol duration also increases. Here's an overview of symbol durations with respect to different spreading factors. If the spreading factor increases by 1, the symbol duration doubles. If the spreading factor increases from spreading factor 7 to spreading factor 8, the symbol duration doubles from 1 to 2. Again, if the spreading factor increases by 1, spreading factor 8 to spreading factor 9, the symbol duration doubles from 2 to 4. If you increase the spreading factor by 1, the symbol duration or sweep time doubles compared to the previous spreading factor. It reduces the bit rate approximately by half compared to the previous spreading factor. The time on air, meaning the message transmission time, increases, which means the distance increases. To give you an idea what the time on air is for a 10-byte payload, let's take bandwidth is 125 kHz. If the spreading factor is 7, the transmission time is 41 milliseconds. But if the spreading factor is 12, the transmission time is 991 milliseconds. LoRa devices uses a higher spreading factor when the signal is weak or there is a lot of interference. Using a higher spreading factor means a longer time on air. If an end device is further away from a gateway, the signal gets weaker and therefore needs a higher spreading factor. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I'll explain what an Snr limit is and how to calculate the receiver sensitivity. For each spreading factor, there is an Snr limit. If this limit is reached, the receiver will not be able to demodulate the signal. This represents the noise floor power level, and this represents the receiver sensitivity, which is equal to the received power when we talk about the Snr limit. The Snr limit is the receiver sensitivity divided by the noise floor power level. In the table below, the Snr limit can be found for each spreading factor. If the spreading factor increases by 1, the Snr limit changes by minus 2.5 dB. To calculate the receiver sensitivity, you can use this equation. S is the receiver sensitivity in dBm. This is the bandwidth in Hertz. This is the receiver noise figure in dB. The receiver noise figure is fixed for a given hardware implementation. For LoRa end-node transceiver chips SX1272 and SX1276, use a receiver noise figure of 6 dB. And this is the signal-to-noise limit in dB. For example, the bandwidth is 125 kHz and the receiver noise figure is 6 dB. Let's calculate the receiver sensitivity for spreading factor 7 to 12. Use the Snr limit from the previous table. Here are the calculated receiver sensitivity for different spreading factors. As you can see, if the spreading factor increases, the receiver sensitivity gets more sensitive. You can see the same values put in this figure. If the spreading factor is 12, it has its highest receiver sensitivity. If the distance between end node and gateway increases, the signal gets weaker, and therefore an increased spreading factor is needed for a lower receiver sensitivity to be able to demodulate the received signal, as you can see in this picture. The spreading factor ranges from 7 when close to a gateway to 12 when far away from a gateway. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain what the LoRa packet format is, how the time on air is calculated, and what adaptive data rate is. The LoRa packet comprises of 3 elements: the preamble, an optional header, and payload. There are 2 types of LoRa packet format modes: the explicit header mode and the implicit header mode. The explicit header mode includes a short header that contains information about the payload length, coding rate, and whether a cyclic redundancy check is used in the packet. The cyclic redundancy check is used to detect errors in digital data. In the implicit header mode, the payload, coding rate, and cyclic redundancy check presence are fixed. In this mode, the header is removed from the packet, thus reducing transmission time. In this case, the payload length, error coding rate, and the presence of the payload cyclic redundancy check must be manually configured on both sides of the radio link. This is a LoRa signal, and this part is called the preamble. The preamble is used to detect the start of the packet by the receiver. The header is the default mode of operation. It provides information on the payload length in bytes, the forward error correction code rate, and the presence of an optional 16 bits cyclic redundancy check for the payload. The payload is a variable length field that contains the actual data coded at the forward error correction code rate, either as specified in the header in explicit mode or fixed in an implicit mode. An optional payload cyclic redundancy check may be appended. When a signal is sent from a sender, it takes a certain amount of time before a receiver receives this signal. This time is called time on air. In this example, the time on air is 530 milliseconds. The total air transmission time of a LoRa packet, aka time on air, aka LoRa packet duration, is calculated using this equation. The time on air is the same as the packet duration equals the preamble duration plus the payload duration. Again, the packet duration is the preamble duration plus the payload duration. In this picture, only part of the payload is displayed. The preamble duration is calculated using this equation. This is the number of preambles plus 4 1/4 times the symbol duration. and this is the symbol duration. For the AU868 band, the number of preambles equals 8 symbols. This is a LoRa signal in the AU868 band, which means there are 8 symbols plus 4 1/4 equals 12 1/4 symbols. Let's check this. There must be 12 1/4 symbols. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 1/4. The symbol duration was already explained in tutorial 15. The symbol duration or sweep time is calculated using this equation. Again, this represents the symbol duration. The payload duration is calculated using this equation. This is the symbol duration in seconds. This is the payload in bytes. This is a spreading factor. This is the cyclic redundancy check. If enabled, this value is 1. If disabled, this value is 0. For LoRaWAN, the cyclic redundancy check is 1. This is the header. If disabled, this value is 1, meaning implicit mode. When enabled, this value is 0, meaning explicit mode. For LoRaWAN, this header is enabled, meaning this value is 0. This is the low data rate optimize. If enabled, this value is 1. If this is disabled, this value is 0. This is the coding rate. For LoRaWAN, the value is 1. Given the potentially long duration of the packet at high spreading factors, the low data rate optimization option can be set to improve the robustness of the transmission to variations in frequency over the duration of the packet transmission and reception. When the low data rate optimization is enabled, it increases the robustness of the LoRa link at these low effective data rates. Its use is mandated when the symbol duration exceeds 60 milliseconds. Note that both the transmitter and the receiver must have the same setting for low data rate optimization. The low data rate optimization is enabled for bandwidth 125 kHz and spreading factor greater or equal than 11. There is an online tool to calculate the time on air. This web page. Let's set the spreading factor to 12. The bandwidth is 125 kHz. Set the code rate to 1. That's the default for LoRaWAN. Change the payload to 10 bytes. Set the preamble length to 8 symbols. That's the default for the AU868 band. The explicit header and the cyclic redundancy check are both enabled for LoRaWAN. As you can see, the time on air is 991 milliseconds. For spreading factor 12, the time on air was 991 milliseconds. And here are the other time on airs for different spreading factors. This graph is based on bandwidth is 125 kHz, coding rate is 1, and the payload is 10 bytes. The blue line represents the time on air for different spreading factors, and here are the time on air values in milliseconds. The red line is the data rate for different spreading factors. The data rate data can be found in tutorial 15, slide 7. And if you look at the data rate at 125 kHz and 250 kHz, at spreading factor 7, you can see that the data rate at 250 kHz is 11 kilobits per second, and at 125 kHz, the data rate is 5.5 kilobits per second. A higher spreading factor means a longer time on air and a lower data rate, as can be seen in the previous graph. A higher spreading factor also means the sender-receiver range gets larger, but it requires more energy, meaning battery power. The LoRaWAN protocol defines the adaptive data rate scheme to control the uplink transmission parameters of LoRa devices. The spreading factor, bandwidth, and transmission power are the transmission parameters. Whether the adaptive data rate functionality will be used is requested by the end nodes by setting the ADR flag in the uplink message. If the ADR flag is set, the network server can control the end node's transmission parameters. Adaptive data rate should only be used in stable radio frequency situations where end nodes do not move. Mobile end nodes which are stationary for longer times can enable adaptive data rate during those times. What now follows is a simplified explanation how the adaptive data rate works. The network server collects the 20 most recent uplink transmission data from an end node, such as data rate and signal-to-noise ratio. Here is an example. This network server collects the 20 most recent uplink transmission data from this end node. For example, transmission data 1 contains this data rate and this signal-to-noise ratio. Transmission data 2 contains this data rate and this signal-to-noise ratio, etc. Of the 20 received uplink messages, the network server takes the maximum signal-to-noise ratio value, which is now called the signal-to-noise ratio measured, and the corresponding data rate. The network server calculates the margin using this equation. For example, the data rate is based on spreading factor 12 and bandwidth 125 kHz. Please note the data rate can be calculated using this equation. As you can see, the data rate only depends on the spreading factor and the bandwidth. The signal-to-noise ratio measured is 5 decibel. The signal-to-noise ratio limit is -20 decibel, which is based on spreading factor 12. More information can be found in tutorial 16. And let's assume the margin default is 10 decibel. The margin can now be calculated, which is 15 decibel. The margin is large, which means the end node uses unnecessary too much battery power to transmit uplink messages. The network server does the following calculation with an optimized data rate. For example, the data rate is now based on spreading factor 7 and bandwidth 125 kHz. It was previously spreading factor 12. The signal-to-noise ratio measured is still 5 decibel. The signal-to-noise ratio limit is now -7.5 decibel, because the spreading factor is now 7. The margin can now be calculated, which is now 2.5 decibel. The margin is changed from 15 decibel to 2.5 decibel, but it can further be optimized by lowering the transmission power. This optimized data rate and/or transmission power are the transmission parameters calculated by the network server and sent to the end node. The end node will use these new transmission parameters to transmit its data and thus using less power. How the adaptive data rate actually works is explained in detail in the LoRaWAN specification. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will discuss the different LoRa chips. LoRa chips can be divided into two types: chips which are used in gateways and chips which are used in end nodes. Semtech owns the LoRa intellectual property but has licensed the intellectual property to other chip manufacturers like Microchip, S3 Microelectronics, and Hope RF. These are the LoRa chips which are used in the end nodes. These values were taken from datasheets, which you can find in this link. The SX1268 is intended for the Chinese market, and the SX1276 is used in many LoRa modules in Europe and United States. Every LoRa gateway has the following two components: a processor to demodulate a signal, and one or two transmit or receive radios. For the processor, you can choose between the SX1301 and the SX1308. And for the radios, the two most common used types are the SX1255 and the SX1257. But there's also another one, SX1258, but it is used in China. A LoRa gateway using SX1301 or SX1308 chip supports up to 10,000 end nodes, and it has 10 programmable reception channels: channel 0 to 7, channel 8, and channel 9. Channel 0 to 7 supports only bandwidth 125 kHz. Channel 8 only supports bandwidth 125, 250, or 500 kHz. And channel 9 is intended for legacy FSK or GFSK formatted signals. The SX1301 or SX1308 chip can scan all 8 channels simultaneously for preambles of all data rates and can demodulate simultaneously up to 8 packets. For example, the first packet spreading factor 7 packet on channel 0 and the 8th packet spreading factor 8 packet on channel 5, which means maximum 8 packets simultaneously. Please note, it cannot do both preamble detection and demodulation process at the same time. These are the LoRa chips which are used in the gateways. These values were taken from datasheets which you can find in this link. These chips are used as transmit or receive radios. This chip is intended for the Chinese market, and these two chips are the processors. This chip is intended for outdoor usage. Look at the operating temperature. And this chip is intended for indoor usage. And here is its operating temperature. The company Hope RF made several LoRa compatible chips. These chips are RFM 95, 96, and 98. More information about these chips can be found at these two locations. These chips can be found in many LoRa modules and can be purchased at Chinese web shops. These are the LoRa compatible chips which are used in EndNodes. These values were taken from datasheets which you can find in this link. The marking W means CE FCC version for overseas market, and without W are meant for Chinese market. These two chips have the same RF96 marking, but this chip is only available in 868 and 915 MHz, and this chip is only available in 433 MHz. This chip is compatible with SX1276 and can be used in the AU 863 to 870 ISM band. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain which LoRa EndNode products are available today and how you can build your own LoRa development board. All LoRa EndNodes must have a microcontroller, for example Atmega32, a LoRa radio module, for example SX1276, and an antenna. There are many LoRa EndNode products available, such as LoRa development boards, where the microcontroller and the LoRa radio module are integrated on a printed circuit board. Here are two examples. Here is the microcontroller, here's the LoRa radio module, and here's the built-in antenna. Here's another LoRa development board. Here's the microcontroller, the radio module, and the built-in antenna. There are also LoRa radio shields to be used, for example, with an Arduino board. This is such a shield. It only has a LoRa radio module and an antenna connector, but no microcontroller. Here is another LoRa radio shield. Here is the LoRa radio module and antenna connector. And this shield has no microcontroller. And we also have LoRa breakout boards. The LoRa radio module is mounted on an adapter plate. This is such a LoRa breakout board. Here is the LoRa radio module, and this is the adapter plate. And here is another LoRa breakout board. This is the LoRa radio module, the adapter plate, and the antenna connector PCB mount. As you can see, the solder connection distance is 2 mm, but the solder connections on the adapter plates have a spacing of 2.54 mm. The adapter plate is needed, for example, to easily mount it on a breadboard. And we also have the LoRa radio modules itself. This LoRa radio module is from the company Hope RF. and this one is from the company Microchip. For educational purpose, I have built my own LoRa development board. It consists of a LoRa radio module, adapter plate, and call antenna, as you can see over here. Total cost is €8.07. It consists of a LoRa radio module. I have used the Hope RF RFM 95 868 MHz. One piece costs €6.98. Next, I have used the ESP8266 Wi-Fi adapter plate, plus 2 pin headers. I have paid 90 cents for this adapter plate. The only reason why this adapter plate is needed is to easily mount it on the breadboard. Next, I needed a copper wire. Diameter is 1 millimeter, the length is 1 meter, and I've paid 90 cents. The copper wire was needed to create this call antenna. How the LoRa radio module, this module, is mounted on an adapter plate, see this tutorial. This tutorial also includes YouTube videos. How the copper 868 MHz call antenna is built, this antenna. See this tutorial. This tutorial also includes YouTube videos. Next, we need additional components such as Arduino Uno. You can also use a clone, a breadboard, jumper wires, and pin headers. The total cost is €5.56. You can buy an Arduino Uno clone for €2.69. The mini breadboard costs 34 cents. You need jumper wires, male, female, length is 20 centimeters, and the pin diameter is 2.54 millimeters. For 40 pieces, I paid 88 cents, but only 3 pieces are needed in this project. Next, you need additional jumper wires, male, length is 20 centimeters, pin diameter is 2.54 millimeters. For 40 pieces, I paid 88 cents, but only 9 pieces are needed in this project. And pin headers, these pin headers. Each pin header has 8 pins, and the pin diameter is 2.54 millimeters. For 10 pieces, I paid 77 cents, but only 4 pieces are needed in this project. 2 pin headers stacked on top of each other, and you do the same on this side, and then you mount the LoRa radio module on the pin headers. This is a self-built LoRa development board. The self-built LoRa development board total cost is €13.63. The development board consists of the LoRa radio module, adapter plate, and call antenna. Total cost is €8.07. And the Arduino Uno, breadboard, jumper wires, and pin headers. Total cost €5.56. The above mentioned products can be found on AliExpress. That's a Chinese web shop. Based on this self-built LoRa development board, I will explain in the next videos which LoRa EndNote library to install on the Arduino board and how to configure it, how to register this LoRa EndNote on the Things network, and how to install a temperature and humidity sensor on this development board. Please note, I assume you have access to a LoRa Gateway. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain the origins of several LoRa EndNote libraries and where these libraries are used. There are several important LoRa EndNote libraries. The Semtech LoRa Meg Node library, the IBM LMIC library. Please note, LMIC stands for LoRa Meg in C, and the Arduino LMIC library. Besides the above-mentioned libraries, LoRa development board manufacturers also created their own libraries to be used on their hardware. Let's start with the Semtech LoRa Mech node library. Semtech maintains a reference implementation of a LoRa endnode. The code can be found at this location. The API documentation can be found at this location. This LoRa node library only supports these platforms. A porting guide is available which provides guidelines on how to port the project to other platforms. See this location. The IBM LMIC library was originally developed by the IBM Zurich Research Laboratory. IBM has ceased development on this library since version 1.6. However, it is provided as open source under the BSD license. The code can be found at this location or this location. This library, however, does not support Arduino platforms. The IBM LMIC library is ported to Arduino platforms and is called Arduino LMIC. This library supports SX1272, SX1276 transceivers and compatible modules such as HopeRF, RFM92 or RFM95 modules. The code can be found at this location and are maintained by Matthijs Kooijman, Thomas Telkamp, and others. The Arduino LMIC library provides a fairly complete LoRaWAN Class A and Class B implementation, supporting the AU 868 and US 915 bands. The compiled size of this library is about 30 kilobytes. The Arduino LMIC library is forked many times, but the fork made by MCCI Catena seems to be actively maintained. See this location. Among others, the MCCI Arduino LMIC has added regional support for Australia, Asia, and India. The Arduino LMIC and the MCCI Arduino LMIC library are intended to be used with plain LoRa transceivers, connecting to them using SPI. This library contains a full LoRaWAN stack and is intended to drive these transceivers directly. The library has only been tested with LoRaWAN 1.0.2 networks. The library cannot be used with full-stack devices like the microchip RN2483. These modules contain a transceiver and microcontroller that implements the LoRaWAN stack and exposes a high-level serial interface instead of a low-level SPI transceiver interface. To understand how the Arduino LMIC library works, read the IBM LoRaWAN in C technical specification, read the Semtech SX1272-73 datasheet, and read the Semtech SX1276-789 datasheet. Here is a global LoRa endnode libraries overview. This is the Semtech LoRa Mech node reference implementation. This is the IBM LMIC library. This library is ported to the Arduino platform and is named Arduino LMIC. And the Arduino LMIC library is forked many times, as you can see over here. And one of these forks is the MCCI Arduino LMIC library. These two libraries supports the SX1272, SX1276 transceivers and compatible modules like HopeRF, RFM92, RFM95. And of course, LoRa development board manufacturers create their own LoRa endnode libraries. Other Arduino LoRa endnode libraries can be found at this location. Please note the following. There are libraries available to set up direct communication between two LoRa radios. These libraries have nothing to do with the LoRaWAN protocol. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will explain how over-the-air activation and activation by personalization works. Before I start with this tutorial, please be aware of the following. The information provided in this tutorial is based on the LoRaWAN 1.0.2 specification. More information about the LoRaWAN 1.0.2 specification can be found at this location. All LoRaWAN specifications can be found at this location. The MCCI Arduino LMIC library has only been tested with LoRaWAN 1.0.2 networks. This is based on the code in October 2018 and has not implemented the LoRaWAN 1.1 new security features. An end device must first be activated before it is able to communicate with the network server. There are two methods to activate an end device in a LoRaWAN network: over-the-air activation, also known as OTA, and activation by personalization, also known as ABP. Both methods will be explained next, but please be aware that it is a simplified explanation. If you need a detailed explanation, please read the LoRaWAN 1.0.2 specification. OTA is the preferred activation method because it provides the most secure way to connect end devices to a network server. Before activation, end devices must know and store its DEF-AUI, app-AUI, and app key. The network server must know and store the same app key. So an end device must store the DEF-AUI, app-AUI, and app key, and a network server stores the app key. Both app keys are the same. AUI stands for Extended Unique Identifier, which is 64 bits long and is generally used for the identification of network components. The DEF-AUI uniquely identifies the end device and is similar to a MAC address. Some devices are already shipped with a DEF-AUI. For example, this LoRa development board has a built-in DEF-AUI. And my self-built LoRa development board has no built-in DEF-AUI. The app-AUI uniquely identifies the application server and is similar to a port number. The app key is an AES, which stands for Advanced Encryption Standard, 128-bit symmetric key, also known as root key, and is used to generate the message integrity code to ensure the integrity of the message. Both end device and network server must store the same app key. The end device generates the def nonce, which is a randomly generated number to prevent rogue devices replaying the join request. The end device constructs a message containing the def nonce, app-AUI, and def-AUI. Over this message, the message integrity code is generated by the app key. Def nonce, app-AUI, and def-AUI are not encrypted by the app key. The end device can now activate itself by sending a join request message to the network server containing the def nonce, app-AUI, def-AUI, and message integrity code. After the network server receives the join request message, it will check if the def nonce has not been used previously. The network server authenticates the end device with the message integrity code value. Because it has received the def nonce, app-AUI, and def-AUI, over this message it will use its own app key, which must be the same as this app key, and calculates its own message integrity code. If both message integrity codes are the same, then this end device is authenticated. If accepted, the following values are generated by the network server. The device address. The device address maps the def-AUI to a network internal shorter address, which is 32 bits long, in order to reduce the protocol overhead in transmitted frames. The device address is similar to a client IP address. The network server also generates the app nonce. The app nonce is a random generated number, and the network server also generates a network identifier. The network server constructs a message containing the device address, app nonce, network ID, and some network settings. These network settings are download settings, which are data rates to be used for receiving. Another network setting is the receive delay, which is the time between transmit and receive. And another network setting is the channel frequency list, which are frequency settings for each channel. Over this message, The message integrity code is generated by the app key. The message itself is encrypted with the app key. The network server sends a join accept response back to the end device containing the encrypted message and the message integrity code. Now both the end device and network server share the same app nonce and dev nonce, as you can see over here. The end device and network server uses the app nonce and the dev nonce to generate two session keys, the network session key and the application session key. The network server sends the application session key and device address to the application server. The network session key is used by the end device and network server to calculate and verify the message integrity code of all data messages to ensure data integrity. The network session key is also used to encrypt and decrypt the payload. The application session key is used to secure end-to-end communications between the end device and the application server. The shared symmetric key is used by the application server and end device to encrypt and decrypt the payload. The payloads are end-to-end encrypted between the end device and the application server, but they are not integrity protected. That means a network server may be able to alter the content of the data messages in transit, but the network servers are considered as trusted. In the activation by personalization mode, there are no join requests or join accept messages sent. The end device does not store the dev AUI, app AUI, and app key, and the network server does not store the app key. Instead, the end device is preloaded with the device address, application session key, and network session key. The network server is preloaded with the device address and network session key, and the application server is preloaded with the device address and application session key. When an end device is trying to communicate with the network server, it will send the message directly. These messages are encrypted and signed. All LoRaWAN devices are forced to encrypt their payload and header with the Advanced Encryption Standard algorithm using 128-bit keys. The LoRaWAN protocol offers two layers of security. On the network layer, the integrity of a message is enforced by the message integrity code using the network session key. The payload is encrypted from end device to network server. On the application layer, the payload is encrypted using the application session key. The payload is encrypted from end device to application server. This means it is possible to have end-to-end encryption of the LoRa data. In October 2017, the LoRaWAN 1.1 specification is out with improved security. As mentioned earlier, the MCCI Arduino LMIC library does not implement the LoRaWAN 1.1 new security features. More information about LoRaWAN 1.1, see these webinars from the Things Network. The missing puzzle pieces of LoRaWAN security, see this YouTube video. And what is new in LoRaWAN 1.1, see this YouTube video. In the next tutorial, I will demonstrate the over-the-air activation method and the activation by personalization method using my self-built LoRa development board on the Things Network. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will demonstrate the over-the-air activation method. In a demonstration, I will use my self-built LoRa development board to send messages to the Things Network using the MCCI Arduino LMIC library. This is my self-built LoRa development board. Make sure an antenna is connected. Go to this web page to see how to create this self-built LoRa development board. The self-built LoRa development board uses the following jumper wire connections between the Hope RF RFM95 LoRa transceiver module and the Arduino Uno. Please note, the Hope RF RFM95 LoRa transceiver module is compatible with the SX1276. Make sure a LoRa gateway is in your area and your LoRa end device can send messages to this gateway. To find a LoRa gateway in your area, you can use this map. Now let's see if there is a gateway near my location. I'm located here and this is my gateway, as you can see over here. But you can also see there are more LoRa gateways in my area. Install the latest open source Arduino IDE. In this tutorial, version 1.8.7 is used. The Arduino IDE can be found at this location. In this tutorial, I assume you already installed the Arduino IDE. Start up the Arduino IDE. Now let's install the MCCI Arduino LMIC library. Select Sketch, Include Library, Manage Libraries. In the search box, enter MCCI. Select the latest version and press the Install button. After it is installed, press the Close button. The Arduino libraries are installed on these default locations. On a Windows environment, in this location. In an OS X environment, the Arduino libraries are installed in this location. And in a Linux environment, the Arduino libraries are installed in this location. I have opened a text editor and I'm going to the Arduino libraries folder. Documents, Arduino, libraries, and I'm selecting the MCCI_LoRaWAN_LMIC_library folder. Open it. Open the project config folder. And here is a file called lmic_project_config.h file. I'm replacing the content of this file with this content. These are my settings. Make changes according to your situation. I live in the Netherlands, so I have to use this setting. And I'm using the SX1276 transceiver module. If you use an Arduino Uno, you must use these settings. The Arduino Uno has 32 kilobytes of flash memory for the bootloader plus uploaded sketch. It is important to use these settings as mentioned earlier. Otherwise, the compiled sketch does not fit the Arduino Uno flash memory. There are more configuration settings which can be overridden by this file. Expand the source folder, expand the LMIC folder, and open the config.h file. In this file, you can find more configuration settings which can be overridden by the lmic_project_config.h file. But in this demonstration, I do not override any of these other settings. Create an account on the Things network, go to this web page, and click the link Sign Up. And just follow the steps. In this tutorial, I assume you create an account on the Things network. After you created an account, log in. Select Console. First, add an application. These are my existing applications. Click this link, Add Application. I have entered this application ID, and I have entered this human readable description. Press this button, Add Application. The application is now created. Now let's register a device. Click this link, Register Device. I have entered this device ID, and in this field you must enter a random value consisting of 8 bytes. You can use this online tool. Press the Generate button and copy the last 2 blocks. Click this button and paste the copy values in this field. And as you can see, there are 8 bytes. After you have entered the device AUI, Press the Register button. Make sure the activation method is over-the-air activation. So this is the device AUI, the application AUI, and the app key. Here's the app key. This picture is from tutorial 21. As you can see, the end device must have the device AUI, app AUI, and the app key. The network server only needs the app key. We will copy these three values to an Arduino sketch. The network server already knows the app key. As you can see, the network server already knows this app key. In the Arduino IDE, select Menu, File, Examples, MCCI LoRaWAN LMIC Library, and select the sketch TTN OTA. Resave this sketch and call it TTN OTA My Demo. Press the Save button. From the Things Network console, copy the dev AUI, app AUI, and the app key to this sketch. Enter app AUI in this field, the dev AUI in this field, and the app key in this field. But watch out, the app AUI and dev AUI must be in little endian format, and the app key must be in big endian format. Big endian and little endian are terms that describe the order in which a sequence of bytes are stored in computer memory. Big endian is an order in which most significant bit, abbreviated by MSB, is stored first. Little endian is an order in which the least significant bit, abbreviated by LSB, is stored first. Here is an example. Here are 5 bytes in big endian format. The most significant bit is located here, and the least significant bit is located here. To convert these 5 bytes from big endian format to little endian format, you only need to change the sequence of these bytes. This byte is moved here, 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 and this byte is moved here. Now these 5 bytes are now in little endian format. Let's go back to the Things Network console. Click this button. You see MSB, but we must use LSB. Click this button, LSB. Do the same for the application AUI. Click this button, as you can see, MSB, and click this button to change it to LSB. Click this button. As you can see, it is MSB, which is correct. Copy these 3 values to the sketch. As you can see, I have copied the app AUI, dev AUI, and the app key in this sketch. Scroll down and make changes to these LMIC pins. Change slave select to 10. Reset is 5. This is data input out 0, data input out 1, and data input out 2. This value is correct, this value is correct, and this value must be LMIC _ unused pin. These settings corresponds with these settings. As you can see, slave select has pin 10, reset has pin 5, data input out 0 has pin 2, data input 1 has pin 3, data input out 2 is not used. And if it is not used, we use the global variable LMIC _ unused _ pin. The Hope RF RFM95 LoRa transceiver module has no RxTx pin, as you can see over here. If you scroll up, as you can see, the message "Hello World" will be transmitted every 60 seconds. Now connect the self-built LoRa development board to your computer using the USB cable. Now is the time to upload the sketch to the Arduino Uno. Select Tools and make sure the Arduino Uno is selected. And select Tools, Port, and make sure you have selected the correct port. Now let's compile the sketch. As you can see, there are no errors. And also note the following: this sketch only uses 53% of the program storage space. The maximum is 32 kilobytes. Now let's upload the sketch to the Arduino Uno. As you can see, the sketch is uploaded to the Arduino Uno, and there are no errors. Open the serial monitor, select Tools, Serial Monitor, and make sure the baud rate is set to 9600 baud. Go to the Things console, select the application you created earlier, select your registered device, this device, reset the frame counters, scroll up and select Data. As you can see, these are the 3 join requests, and this is the Hello World message in hexadecimal format. As you can see, every 1 minute a payload is sent. If you click on this icon, you will see more data. You can see all the gateways where this message is sent to, this gateway and this gateway. And you can also see the estimated airtime. What I will now do is keep this sketch running for 15 minutes, and I will copy all this data into a text file. You can find this text file at this location. At this moment, my gateway is up and running. My end device is only 8 meters away from my gateway. Here is an interesting question. Do I comply with the ETSI duty cycles and the Things Network Fair Access policy if I keep running the TTN OTA my demo sketch for a day? Well, this question will be answered in the next video. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In tutorial 22, I transmitted the message Hello World every 60 seconds using the sketch TTN OTA My Demo. At the end of that video, I asked the question, do I comply with the ETSI duty cycles and the Things Network Fair Access policy if I keep running the sketch for a day? In this tutorial, I will answer that question, and I also will explain what the transmission time interval is and how it is calculated. In this tutorial, I will only focus on the ETSI duty cycles and in particular, the duty cycles which applies in Europe. Please do your own research and check which duty cycle regulations, if any, applies to your country. In tutorial 11, I have explained that ETSI divides the 863 to 870 MHz band into 5 subbands, G, G1, G2, G3, and G4, and each subband has different constraints in terms of EIRP, duty cycle, and channel bandwidth, as you can see in this table. Here is a better overview. You can see the different subbands and the corresponding duty cycles. This slide is already discussed in tutorial 11. In tutorial 22, I have demonstrated how to transmit the message Hello World every 60 seconds. The metadata displayed in the Things Network console during the demonstration can be found at this location. The relevant metadata can be found in this table, such as frequency and data rate. As mentioned in tutorial 11, an end device changes channel in a pseudo-random fashion for every transmission. In Europe, for uplink transmissions, 8 different frequencies are used. And here is the proof. The frequency changes for every transmission, and all 8 frequencies are used. These 8 uplink frequencies. In Europe, for all 8 frequencies, the duty cycle is 1%. This means the total allowed uplink time on air is 864 seconds per day per device. And please note, a day has 86,400 seconds. The Things Network Fair Access Policy is there to make sure that the community network is not abused by large deployments and applies to all of the community network. More information about the Things Network Fair Access Policy can be found at this location. If you scroll down, you can find the Things Network Fair Access Policy here. The Things Network Fair Access Policy limits the data each end device can send by allowing an average of 30 seconds uplink time on air per day per device, and at most 10 downlink messages per day, including the acknowledgements for confirmed uplinks. Compared to the ETSI duty cycles of 1%, the Things Network Fair Access Policy is more restrictive because it only allows an average of 30 seconds uplink time on air per day per device. This is equivalent to a duty cycle of 0.0347%. If you look at this picture, for every transmission, there is a waiting period, which is called the transmit time interval, and the message time on air. N is the number of transmissions within a day. Based on this picture, you can create this equation. The transmit time interval plus the time on air times the number of transmissions within a day equals 86,400 seconds. This equation can be rewritten like this. The definition of a duty cycle is this. A duty cycle is the fraction of one period in which a signal or system is active. In this picture, the period is a whole day. So the duty cycle is the number of transmissions times the time on air divided by 86,400. The time on air is the time the message is being transmitted. This is example 1. If the duty cycle is 1% and the time on air is 0.05 seconds, the transmit time interval is 4.95 seconds. This is example 2. If the total uplink time on air is 30 seconds per day per device and the time on air is 0.05 seconds, then first you calculate the duty cycle, which is 0.000347722. The transmit time interval will be 143.95 seconds. So the question was, do I comply with the ETSI duty cycles and the Things Network Fair Access Policy if I keep running the TTN OTA My Demo sketch for a day? Please note, in the sketch, the transmit time interval was set to 60 seconds. As you can see, the transmit time interval is set to 60 seconds. So here is the answer. I only need to focus on the Things Network Fair Access Policy because it is more restrictive. The Things Network Fair Access Policy uses a total uplink time on air of 30 seconds per day per device. The time on air was 82.432 milliseconds. As you can see here. First we calculate the duty cycle, and then we can calculate the transmit time interval, which is 237.32 seconds. So yes, I will break the Things Network Fair Access Policy. In the TTN OTA My Demo sketch, the transmit time interval is set to 60 seconds, but it should be 238 seconds. The above-mentioned calculated transmit time interval does not change as long as the payload length and data rate does not change. So let's assume the following situation. My gateway went down and the nearest gateway my end device can send messages to is 5 kilometers away. So the data rate changes to spreading factor 12, bandwidth is 125 kHz, the code rate and the payload length remains the same. So what is the new transmit time interval when using the Things network? First we calculate the time on air using this online tool. The spreading factor is 12, the bandwidth is 125 kHz, The coding rate is 4/5. The payload length is 13 bytes. Preamble length is 8, and the explicit header and CRC are enabled. The time on air is 1155.07 milliseconds, and we can send a message every 1 minute and 56 seconds. But please note, this transmit time interval is based on a duty cycle of 1%. The Things Network Fair Access Policy uses a total uplink time on air of 30 seconds per day per device. Again, we calculate the duty cycle, and now we can calculate the transmit time interval. This is a time on air we calculated with the online tool, and this is the calculated transmit time interval. This means for every message transmitted, we have to wait 55 minutes and 25 seconds before we can transmit again. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will demonstrate the activation by personalization method. I assume you have watched tutorial 22, and based on what I have done in tutorial 22, I will continue where I left off in that video. Make sure a LoRa gateway is in your area and your LoRa end device can send messages to that gateway. In tutorial 21, I have explained the difference between over-the-air activation and activation by personalization. In the activation by personalization method, the end device must store the device address, application session key, and a network session key. The network server must store the same device address and network session key. Go to the Things Network, log in, select Console, click on Applications, select the YouTube demo application, and register a new device. Enter a unique identifier, for example, YouTube_demo_device2. Enter a device AUI. It is a random value consisting of 8 bytes. I use my online tool. Press the Generate button. Copy the last 2 blocks. The code is pasted in this field. As you can see, it is 8 bytes long. Press the Register button. In this screen, select Settings. Change the activation method to ABP. As you can see, the device address will be assigned by the network server, the network session key will be generated, and the application session key will be generated. Press the Save button. These 3 values must be stored in the end device. The device address must be in a hexadecimal format. The network session key must be in big endian format as a 16 bytes array. Click this button. 16 bytes array, big endian format. The same applies to the application session key. Big endian format, 16 bytes array. These 3 values needs to be copied to our new Arduino sketch, which I will explain in a moment. In the Arduino IDE, select Menu, File, Examples, MCCI LoRaWAN LMIC library, and select the sketch TTN ABP. And resave this sketch. Save it as TTN ABP My Demo. Copy the network session key, application session key, and the device address from the Things console to this sketch. As you can see, I have copied the 3 values from the Things console to this sketch. These 2 values must be in big endian format, and the device address must be a hexadecimal value and not an array. Prefix it with 0x to indicate that this is a hexadecimal value. Same as in tutorial 22, the message Hello World is transmitted every 60 seconds. If we use this transmit time interval, we will not comply with the Things Network Fair Access Policy. If we run the sketch for more than 24 hours and the data rate is spreading factor 7, bandwidth 125 kHz, or even worse, spreading factor 12, bandwidth 125 kHz. Please do the calculations yourself. Make the same pin mapping changes as explained in tutorial 22. Slave select is 10, reset is 5, DIO 0 must be 2, DIO 1 must be 3, and DIO 2 must be unused. Comment out these lines. Now connect the self-built LoRa development board to your computer using the USB cable. Now select the correct board, select Menu, Tools, Board, Arduino Uno, and select the correct port. Select Menu, Tools, Port, this port. Compile this sketch. As you can see, there are no errors. Now upload this sketch to the Arduino Uno. As you can see, there are no errors. Open the serial monitor. And set the baud rate to 115,200 baud. Go to the Things Network console, select the app YouTube Demo app, select the registered device, YouTube_demo_device2, select Reset Frame Counters, and select Data. As you can see, the message Hello World is received by a gateway and sent to the network server and displayed in the Things Network console. Please note, there is no join request message sent. As you can see, every 1 minute the message Hello World is sent. As you can see, we are using the application by personalization activation method. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them. In this tutorial, I will demonstrate how downlink messages are sent from the Things network to my self-built LoRa development board using the MCCI Arduino LMIC library. I assume you have watched tutorial 22. In that video, I created the TTN OTA My Demo sketch and demonstrated the OTA activation method. For security reasons, in the TTN console, the registered device YouTube demo device, the dev AUI and app key are modified. To keep these videos as short as possible, in this tutorial I already have resaved the TTN OTA My Demo sketch and called it TTN OTA Downlink and changed the dev AUI and app key accordingly. Make sure a LoRa gateway is in your area and your LoRa end device can send messages to that gateway. Open the Arduino IDE. So the TTN OTA My Demo sketch is resaved as TTN OTA Downlink, as you can see over here. For security reasons, I have altered the dev AUI and the app key. Please note this sketch still transmits the message Hello World every 60 seconds. The TTN OTA download sketch needs to be modified. Go to this link, and this is a modified TTN OTA download sketch. Search for the word Edit and copy and paste these codes in the TTN OTA download sketch. The same applies for this code, and the same applies for this code. To detect the received download messages, two LEDs, green and yellow, including 220 ohm resistors, are connected to the Arduino Uno. as you can see over here. This setup is the same as in tutorial 22. In this tutorial, I only added 2 LEDs with resistors. The anode of the green LED is connected to pin 6. The anode of the yellow LED is connected to pin 8. And both cathodes are connected to ground. So the hardware setup looks like this. Now connect the self-built LoRa development board to your computer using the USB cable. In the Arduino IDE, select Tools, Board and select Arduino Uno. In the Arduino IDE, select Tools, Board and select your port. Compile and upload the TTN OTA download sketch. You should not see any errors. In the Arduino IDE, select Tools, Serial Monitor and select baud rate 9600. The device is being registered. The Hello World message is received. As you can see, every 60 seconds the message Hello World is transmitted. Click Overview, scroll down. In the download section, select bytes and enter the value 01 and press the send button. Select data. As you can see, the payload 01 is scheduled. As you can see, the yellow LED is now on. Go to Overview and enter the value 02. Press the send button. Select data. As you can see, the payload 02 is scheduled. As you can see, the green LED is on. So if you send the hex value 00, both LEDs are off. If you send the hex value 01, the yellow LED is on, but the green LED is off. If you send the hex value 02, the yellow LED is off, but the green LED is on. And if you send the hex value 03, both LEDs are on. The Things Network Fair Access Policy allows at most 10 download messages per day, including the acknowledgement for confirmed uplinks. More information about the Things Network Fair Access Policy can be found at this location. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them.